So now I'm starting the lecture. So welcome back, everyone. Yeah, so we are starting the last lecture on the clustering section of the course, and so this one's going to be on a technique called mixture of Gaussians, which is going to give a bit more of a statistical flavor interpretation to these clustering problems, and hopefully tie back a little bit to the first few sections of the class where we talked about some of this stuff. But it turns out the basic approach is just going to build on the Lloyd's algorithm that we and the assignment-based clustering we've talked about the last couple of lectures. And I'll probably finish up by diving a little bit into a technique called mean shift clustering, which is going to be a completely different way of clustering, just to give you a flavor of how different the notion of clustering can be, other than the main stuff we focused on. There are even more kind of variants that are talked about inside the book, for those of you interested in diving more, or there's the data mining class, or we often offer a graduate level class on clustering that goes into even more details on this stuff. So before I get into that, let's look at the schedule here. So number one, quiz 5 was so on Monday. I think the scores were a little bit lower than I hoped, but we haven't finalized all the point totals on this yet, so we'll see. So if that's the case, I'll try and make the final quiz a bit easier to even this sort of stuff out. But it also gives me a sense that kind of the kind of dimensional reduction stuff is stuff that can be kind of hard to get a handle on this. So it might be something I'll focus a little bit more on in the review at the end of this semester. And then the homework 4 is due today, or was assigned to be due today. I decided last night to push it back by 24 hours. So this will now be due tomorrow at 1:10. So 1:10 p.m. So just 24 hours push back from when it's usually due. That means you can ask us a bit more questions. It's a crazy year. I know this is one of the harder homework. So, it's not a good time to teach a lesson to all of you about deadlines, and instead rather you kind of get a bit longer to polish this up. And then we're working on homework 5. We'll hopefully get that posted, maybe the end of the week, if not in the early part of next week, so you can start working on that. And then we'll see we're finishing up the clustering section of the course, and then we're going to go on to classification, which is kind of the thing about what machine learning is all about. So if you took this class to know more about machine learning, you're finally going to be, I think, ready to kind of dive into that. And we'll get we'll really understand the basics very well, but it is a super broad field, and there's no way I can cover all of it, but you will get kind of a flavor and understand the terminology and how the basic sort of stuff that works. You'll see kind of one of the most basic algorithms, how to solve it as well. So since this pushback, our late assignment is still accepted. So that means that on homework 4, the late penalty clock will start at the due date on Canvas, right? So whether you will, you can always turn it in up to 1 or 2 days late and get 10 or 20% penalty on the homework. And that timer of when it's 10% or 20% will start based on the Canvas due date. So I pushed that back as well. Yeah, so just, not gonna try not to worry too much about deadlines. I gave a couple of kind of a number of personal extensions, because that, in a normal year, there'd be like 1 or 2 of these a semester. This year, there's a whole bunch. And I'm sure some people have had some issues that they're just not bothering to tell me about. So yes, let's just push everything back one day, and hopefully this is useful. If you're done, you can turn it in. If you want some more time to finish it, then great, go ahead and do that. So okay, yeah. So okay, so let's go and get into the lecture. Great. So clustering and mixture of Gaussians. All right. So let's start by reviewing the clustering kind of framework as we've been looking at. This is the assignment-based clustering, where the input is X is going to be a subset of RD, and we're going to stay in RD all the lecture today. If you go to the data mining class or other places, you'll see stuff where it's not in RD so much, but it means we're going to have a distance between these, and this distance between X1 and X2 is just going to be the Euclidean distance. Okay, and we're going to maybe tweak this. You can think of it as so Mahalanobis distance in some points, if you know what that is. If not, we'll just be kind of scaling stuff a little bit with the mixture of Gaussians. So we'll get into that. But basically, the underlying distance we're assuming is the Euclidean distance here. Okay, and we're also given as K equals the number of clusters. Okay, and then the output is going to be a set of sites S, S1, S2, up to SK. Okay, and these are going to define the clusters. These are going to be kind of the centers of the clusters. And we're going to tweak a little bit what this means by these sites. We're going to think of these. Today, we're going to tweak this to a set of, let's say densities, okay? F1, F2, up to Fk, okay? And I'll build up and explain what this means, but they're kind of going to still have a center point to them. So I haven't changed very much yet, but just kind of want to review Lloyd's algorithm a bit here, because because the mixture of Gaussians is going to kind of, the algorithm we're going to use is going to build directly on top of this. Okay, so we're thinking of having, and if remember, we have this data, which may have looked like this, and our goal is then to find these kind of three sites, say S1, S2, S3, and these kind of define the partition of the data into these subsets here. This will be correspondingly, this will be X1, X2, X3, where this will be our clusters, the output, okay? And we do this by Lloyd's algorithm, okay, which was to, it's going to kind of repeat on two steps. Assign each xi to closest sj, and to b to center sj, this each of the sites, to the average of each of the elements in the site, right? So if I take a look at these objects over here, and I take the average of them, that's going to be the reassignment of S2, right? So if I alternate between these steps, I guarantee that the sum of the squared errors of the matching of each point onto the cluster center is going to decrease every step here. And so this is going to, converge to a solution, which might not be the optimal solution. As we saw, it could get stuck in a local minimum, but it's going to work pretty well most of the time, and there are a couple tricks to deal with the rest of this. Sure. So okay, so to build up to mixture of Gaussians, I first want to talk about kind of a variant of this called soft clustering. Okay. So soft clustering is a variant on this formulation where I'm not being so strict of each site has to be exactly onto each item has to map exactly onto one of the sites. So this allows partial assignment of kind of xi onto the sites sj. Okay, so I don't say each site like x7 has to be on site 2. It could be partially on site 2 and partially on site 1. Okay, so I'm not quite sure. I don't want to really draw a line. It's like, you know, you don't want to cut the calf in half to give it to both people. You want to say, or to, you know, to give it to one or the other. You kind of want to split it, or I guess you do want to cut the calf in half. I guess that's the wrong analogy there. But so here, I'm going to draw a picture, and hopefully this will make a bit more sense. Okay, so let's say I have sites S3, S2, and S1, and with these I've got this Voronoi diagram, which describes how I typically would partition the data. Okay, and if I have some points up over here, then they're going to be on site 1. That's going to make sense. These sites probably be on, these data points are going to be on site 2, and these are probably going to be on site 3. But then if I have a point here, and in the book I call this example x3, okay, now I'm like, well, technically it's on one side of the Voronoi diagram. I should assign it to site 2, right? But it's pretty close to this boundary. It's not too far of a distance between site 1 and site 2. I could easily change my mind and say that I'm going to kind of do this onto site 1 instead, or at least it might be site 1. I'm not so sure, you know. And then it could even have an example here, x7. That's kind of, you know, it's technically closest to site 3, but it's not that much further from site 2 or site 1, right? So I want to give these a partial assignment. Okay. Okay, well, I want to a little bit more space on the slide. So let me do some little magic here. Okay. Okay, so I want to think about how we would store this in a computer. If we were to implement kind of this assignment-based clustering, the way I would implement it, I would implement it as just an array, as kind of this array. And I would say cluster index. Okay, and so basically, implicitly, you've got this array, right? And it has the point number. So let's say I've got 1, 2, this is 3, 4, 5, 6, 7, 8, 9, 10. Okay, and so I just store in here, this is implicitly point 1. It's mapped to site 1. Point 2 is mapped to site 1. So I just store the index of the site it's mapped to. X3, okay, this one is assigned to site 2. 4 is assigned to 2. 5 is assigned to 2. 6 is assigned to 2. 7 is assigned to 3. 8 assigned to 3. 9, 3, and 10 is assigned to 3. Okay, right? So this is how I would store it. I would just keep an array. I know how many points I have. I just store the index of which site it's assigned to, and I would store an auxiliary structure of the information about the actual sites or the cluster representation. Okay, but if I want to do a partial assignment, I want to think about this somewhat differently. For the partial assignment, I want to think about a probability assigning to each of the clusters. probability 1, probability 2, and probability 3. And so I'm going to think about instead having 3 arrays here. Okay, and so for each of these, for each point, right, so I'm going to have the same indexes on these points. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I'm going to do a partial assignment. Okay, so for point 1, it's maybe in this case it's going to be entirely on index 1, so it's 1, 0, 0. So probability assigned to point to site 1 is 1, right? That's for the index of the point 1. For index of point 2, it's going to be the same, right? These are very close to point 1 over here, right? That's what these guys over here. But for site 3, this might be a little bit different. I might say, well, maybe point 4, it's assigned to site 1, and point 6, it's assigned to site 2, and 0 probability site 3. Okay, so I'm going to enforce that this representation is a probability distribution over what site it's assigned to. I kind of split its assignment up in this way, right? So I get this partial assignment. And here I'm going to get 0, 1, 0, 0, 1, 0, 0, 1, 0. And then for site 7, right, is again going to be the split. It's probably mostly to site 3, but I'm going to partially, so 30% site 1, 30% site 2, right? So this is 30%, this is 30%, and this is 40%, right? Because it's kind of near this boundary, right? So I want to do some probabilistic thing here, and then these might be entirely assigned to site 3. Okay, so this is just an example of how I would do this, right? How do you assign these probabilities? Okay, we're going to get into this next with mixture of Gaussians. It'll give us a formal way of thinking about these sort of things. That's one way to assign the probabilities. There's one kind of other clever way I think some people find a lot of good use out of that's more combinatorial and uses the Voronoi diagram. What I can do is I can, how do I assign these probabilities? One way is I could pretend that, let's say that's object X7 was a new site, okay? Now that's going to change the Voronoi diagram because I'm going to draw these bisectors here, okay? Okay, it goes off in this way, okay? And now it's going to give me some region. This region is typically going to be internal region. It might be inside of a box. And now I'm going to say, look at this particular, fill in this region here, and say what fraction of that used to be within site X, site S3's Voronoi region, right? So what fraction of the yellow region is the orange region, and that's the probability. That's one way people use. This is useful in very dense terrain things when you have kind of non-uniform cover, but it kind of gives you a nice combinatorial way of doing this. Okay, but we're going to go back and do a statistical view. This is just a taste that there are multiple ways to do these partial assignments. But hopefully this kind of makes sense. If I don't want to completely partition my data, then I can do a soft clustering and do a partially point. The interesting ones here are point 3, which is this one, is partially assigned to these 2 points, and point 7 here, is partially assigned to all 3 of the points. It could be that all of them are partially assigned, just most of the values are close to 0. In this case, I've snap them onto probability 1 being a site, which is probably more convenient. So yes, okay, so this idea of soft clustering, it's this taste of the many kind of complex ways the notions of clustering can deviate from what we've talked about so far. Okay. Okay, hopefully that general concept makes sense. Okay, so I want to get back to the main focus today, this idea of mixture of Gaussians. And so this is the idea that we're basically going to be doing soft assignment clustering, and we'll get to the soft assignment part kind of gradually. But the idea is I'm going to have, you can interpret this formulation as a slightly different, something other than clusterings. So think of the input as the data in subset of RD, and I'm going to have K, which is going to be in this case is going to be the number of so Gaussians. Okay, and I want to, now I can think of the goal as to find the best kind of so distribution that X so likely was drawn from such that it is composed of K so Gaussians. Okay, so kind of the idea is if I draw this in 1D and I've got some data that kind of looks like, like some data points here, then I might want to try and fit this as these 3 Gaussian distributions. And so kind of, I want to say, if I have data, I want to try and fit a probability distribution on here, and I want it to be the sum of, or the mixture of 3 of these Gaussian distributions. And you could think of, okay, I decide which Gaussian distribution I'm going to choose from, and this might not be a uniform, and then I'm going to draw a data point IID from that Gaussian, right? I think we talked about generating Gaussian random variables. You could think of, and assume that's how the data was drawn, right? What is the maximum likelihood estimator of what is this K Gaussian distributions given that this data I've seen, right? So I'm going to be given this data X, right, which are the points, and I want to fit 3 or K Gaussians on top of that, so those fit the data pretty well, right? If I have 1 Gaussian, we've actually talked about how to do this before. It turns out the maximum likelihood estimator is that I take the mean of all the data and I represent the Gaussian with the center of the Gaussian at the mean of the data, right? This was assuming that we knew what the standard deviation was. Okay, so if we kind of talked about this in 1D. Turns out that trick extends to multiple dimensions as well. Now we're going to say we want to fit K Gaussians. There's K different types of data. Effectively, you want to fit K Gaussians to them. We're not told which data point comes from which data, the same way as in clustering, right? So when we get this out, then we kind of say, well, I can then look at one of the data points and say, okay, this data point probably corresponded with, there are 3 clusters here, and this one is most likely assigned onto this one, so it probably came from that distribution. Okay, but we're going to do this from this kind of, probabilistic view of what's going on there. So we try and formulate this. I think it's going to be useful to first say what is a Gaussian distribution, and Gaussian distribution. And remember, this is going to be a probability distribution. And we're going to write it a bit more in a bit more powerful way than we had earlier in the semester. It's going to have a mean to it, and it's going to have a covariance matrix. The covariance matrix will be represented by sigma, an uppercase sigma, which looks kind of like a sum, but if you were to write it in LaTeX, and that looks a lot like, it looks a lot like sum, but those are different symbols in LaTeX. Okay, so it's going to be sigma here. And so this will give a value for every kind of interpretation x. And in this case, we're going to have that x is in RD, and it's going to be a probability distribution. So if I integrate over RD, this function, the integral is going to be 1, right? Remember, we spend all this time talking about probability distributions, and why did we do that in this course? This is one of the reasons. Okay. Okay, so I'm going to define this, and it's going to have some, and I'm going to do this in general for d dimensions now. I don't think we did this, not sure if we did this earlier in the class, but it's going to have these coefficients in front. That's going to ensure that the integral is 1. And these are kind of, and this is going to include, so it's 1 over 2 pi to the d over 2, and it's going to be 1 over the determinant, or square root of the determinant of the of sigma, which is going to be this covariance matrix, and I'll explain where that comes in shortly. The determinant, hopefully you've seen before. I'm not going to try and define it. It's kind of like a norm operation, but it's a bit different. I'm pretty sure it is described in the book, but we didn't talk about it in the lecture, or you can look it up on Wikipedia. It's got kind of a tedious explanation. But think of it as a size. It's measuring some size quantity. Okay, and then the general part is the x. This is e to some power, right? So this is e to the power that's what x represents, if you remember that. And this is minus 1/2 times x minus mu. Mu is this mu. This is kind of like a mean. This is going to be a point in RD. Okay. Transpose. This is the sigma. Okay, sigma operator. That's an inverse here. X minus mu. Right. Okay. All inside the x. Okay. So this is the notion of a Gaussian distribution. It's basically e to the power. And then it's got, so this term, this is basically going to be a distance determined by this sigma between x and mu. It's basically a distance, the square of a distance here. Okay, and I'll give a little bit of intuition on what this is doing. Okay. So this is how you define a Gaussian, and this allows it. Before we had talked about you think of you have some domain with an origin, and you pick a point mu, and then we had these Gaussian distributions which were essentially symmetric. As you get further out, the function value got lower, it kind of decreased as it went further out. What this allows us to do, when I have covariance, when I have this this covariance matrix now, it allows it to, you still have a mean mu, which is the center of what's going on, but it's going to have some sort of kind of skew to it. Right? So the skew, and this should actually look like some of the pictures we drew with respect to the with PCA. You can these are going to be these ellipses, and they're going to have an axis to the ellipse, and these axes are going to kind of be like the principal components of some data, the distribution that this is representing here. Okay, but this covariance allows it to have this kind of skew in how it fits the data. So now if our data is kind of along some weird axis, we want to build that into a cluster, and for the Gaussian tool, we're able to do that with this kind of fit a Gaussian on data which is not kind of like circular. If it's kind of an elliptical on a weird angle, we can now kind of describe that with this sort of Gaussian distribution. Okay. I'm going to start though by saying, kind of just to understand this green equation a little bit more, let's say the case where this covariance matrix is the identity. All right, that's going to actually correspond with this circular case. Okay, but let's go and see what happens with this formulation. Then I'll just look at the e to the exponential part of this. This can be minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, and now if I replace this guy with the identity, then the inverse of the identity matrix, remember this is all ones off the diagonal, and the property of the identity, or the inverse, is that I multiply sigma inverse times sigma, I get the identity matrix. Well, that means the inverse of the identity is the identity. And if I multiply a vector by it, it's not going to do anything. It just keeps it does not change this vector. So when I have this as the identity matrix, this sigma, the covariance here, then this is just going to be mu x minus mu transpose. The identity disappears, x minus mu. Okay, and now I'm multiplying two vectors together, and and when I write it, the transpose times the vector itself, this is really just, that's one of the ways you can write the dot product. Right, so this is really the dot product between x minus mu, comma x minus mu. Okay, and the dot product of a vector with itself is just the norm squared of that. So that's x minus mu squared. Okay, so this goes back and looks like the form of the Gaussian that we had before, but it doesn't have this 1 over lowercase sigma. You know, we usually have 1 over 2 lowercase sigma before. This is divided by 2. There's a minus times sigma, which is equal to 1 in this case squared, right? So if I had sigma equals to 1 before, then that sigma disappears, right? But this was the form we had it before. And so this is just the case when I don't have any scaling at all, then I'm recovering what we had before in this Gaussian interpretation. Okay, so and what this sigma matrix is doing, okay, so now I guess I should say that sigma is going to be a d by d matrix here. Okay, so this is a d by d matrix. And so what this is doing is it's telling me this skew that I'm putting on here, how I'm stretching this Gaussian. Okay, and so this is the covariance. It tells me how two of the coordinates vary with each other. So this simple version of this is going to be sigma is going to look like sigma 1, sigma 2, up to sigma d. And these are all going to be it's all going to be zeros off the diagonal. And then those are going to act like the eigenvalues or the singular values. And it's going to tell me how much to scale each of these directions, right? So if I have, if my covariance equals sigma 1, sigma 2, sigma d, and there's zeros elsewhere, then what this is going to do is it's going to give me then the Gaussians I'm going to consider are going to be these elliptical shapes, but they're going to be stretched particularly along the axes. So this is the size, the amount of stretch here might be sigma 1, right? The amount of stretch here might be sigma 2, and sigma 1 might be larger than sigma 2 here, right? Maybe sigma 1 is bigger, so it's stretching more on this axis. Okay, but remember I did an inverse. There's an inverse here, so that I'm kind of dividing by the stretch. So that means that if I'm dividing by it, that means that the distance actually can travel faster in those directions. Okay. Okay, so now that's if it has the simple covariance where there's no correlation. Because I have a 0 here, this is no off diagonal. So no off diagonal, so covariance. And that means if I move in one direction, it doesn't tell me anything about the movement in the other direction. These are independent now. But you know, as I mentioned, I want to be able to capture data which kind of looks like this, right? I have data which is kind of correlated on some diagonal, and I want to be able to capture it with a shape that kind of looks like this, right? So in order to do that, I can't do that by just stretching on the coordinate axes. I have to stretch on this other axis. And so in order to do that, I need to basically do like PCA, right? So I have to do PCA, and so that means I have to kind of change a new basis to tell me how to scale. So I need a covariance where where this elliptical thing is scaled is not the coordinate basis, and that means it's not going to be just the diagonal, but there's some other stuff going on. So I could, if I did decompose sigma by the SVD, right? If I did do the SVD on sigma, I would get that it's a square matrix, so I can do the eigen decomposition. But I would get that the eigenvalues would be V1 and V2, and then the amount of scale, the eigenvalues would tell me how much it's stretched in that way. Okay, so that's kind of how to think about this covariance matrix, what it's telling us here. Okay. Okay, so now I have this definition. This is the probability definition, but probability distribution definition for a Gaussian distribution. And now I'm going to have data that doesn't look just like one of these ellipses, but it's going to be several of them. They might not all be the same orientation. So I could have, in the same data set, I could have another ellipse that looks like this, right? Another cluster of my data. I want to fit both of these in the same clustering, right? So I want to fit this with function 1 and this with function 2 to describe my data, right? And so I'm going to describe this as f sigma 1 or mu1 sigma 1. So remember my mu1 is here, and then the sigma is going to be captured by the amount of the skew, and this one is going to have sigma 2, and it's going to have say V1 and V2, which is capturing this sigma symbol. I'm not going to need the actual singular vectors. This is just a way to help think about it. Okay, so I want to capture this data by these two functions. How do I fit these best two Gaussian distributions on top of this data set, which I found, right? And this is the mixture of Gaussian problem. Okay. So let's do a first formulation of this, and we are going to modify this later. And this is an MLE, hard mixture of Gaussians. Okay, so I'm going to try and write this down as a optimization problem. So I'm going to given x and k. I want to find kind of F1, F2 up to Fk. Each of these are in the space of these Gaussians, and I want to maximize. So I want to maximize the function, the maximum likelihood function, right? The maximum likelihood is the product. Right? It's the product over all of the data points I have. And for each of them, I'm going to assign it. I'm going to evaluate it with some function fj of x. I'm going to assign I'm going to evaluate it. Use fi. I'm going to use fi of x. I'm going to do it on the max fi in my set. Right? So I'm going to have this set of these functions. So I'm going to find a set of these functions, k of them, and for every data point, I'm going to assign it to the one that has the highest likelihood, right? Which is kind of like the closest one, but that allows me to skew the distances, right? So if I go back here and I've got this kind of mysterious point right here, let's say, some point right there. Well, is it closer to mu1 or to mu2? Well, it might be a little bit closer to mu1, but if I'm looking at how far I have to stretch the probability distribution, then this might be closer to the F2. That might give me a closer match with this point, because it's in the direction where I have more variance in F2 than I did in F1. Okay, so it allows me to find the distribution which maximizes this, right? So I want to have k of these distributions, and I want to find them so that every point I assign to the best fitting one, and I say, okay, so I want for all the data points that they are going to be from one of k distributions, and I want to say what's the product of the likelihoods that they were from one of these distributions, right? And that's what this is. This is a maximum likelihood. This is an MLE formulation, maximum likelihood estimator. Okay. Okay, so again, now I want to point out, if I look at this formulation, and if I force that H sigma I is going to be the identity matrix, okay? So that means that each Fi is going to be equal to an F mu I identity of X, which is, there's some coefficient in front, but that's all going to be the same coefficient, minus X minus mu squared over 2, right? So if they all have the same thing, then if I maximize this, it's the same as minimizing this, so distance, right? So I can say that this is equivalent to, so minimize mu1 up through mu k, and I'm going to go through this log transform, right, which is the sum of x and x min mu I in this set F, right? All the covariants are the same, so I just can parameterize them by the centers. And this is the natural log of F of I of x. Write that a little more clearly. F of I of x, which is going to be equal to minimize these mu I, the sum of x and x of the minimum mu I of f. And if I take the negative log of each of these, because I've this negative allowed me to turn the max into a min, right? But if I take the natural log of an exponent, right? If I take the natural log of this exponent over here, then the natural log and the exponent cancels, the minus signs cancel, and I'm going to get x minus mu I squared divided by 2. And this is exactly the k-means so objective. Okay, so I've recovered the k-means objective from the statistical point of view. Okay, so if I fix the covariance, then then these are all kind of all the Gaussians I'm fitting are coming out in a circular way. So the one that's going to have the maximum likelihood, if they all have the same covariance, the whole same scaling, is just going to be the closest one. An assignment to the closest one goes back to the FoDA diagram, and I'm going to exactly, and then the cost function, by doing a log transform on the maximum likelihood estimator, the negative log likelihood is going to be exactly the sum of the squared distances again, which is the k-means formulation. Okay, so a special case of this, again, this is going to be a kind of a special case, right? So I'm forcing this special case here. And I'm also doing this hard assignment, which will take off here. These are two assumptions I put on. I'm going to remove these, and we're going to get kind of more powerful statistical framework. But if I force these assumptions that all the covariances are the same, and I do a hard assignment, then I recover exactly the k-means formulation, and I can use Lloyd's algorithm. Okay, so far we've got some version of this which we know how to solve, and now I'm going to kind of extend this a little bit. Okay, so there are two steps we need to do to extend this to do kind of this the right way. Let's see, which one do I want to do first? Yeah, so let's first do, how do I estimate the covariance instead, right? So I know, so I could run, just hold on, I'll write down a bit later the exact way we extend Lloyd's algorithm. But I could do this max, I could do this formulation. I could compute this. Instead of minimizing the distance, I could just find the assignment to a distribution defined with a non-trivial covariance that maximizes this, right? This shouldn't be too hard to do. I just compute all of the likelihoods and I find the one which is maximized, right? So, but how do I, once I know the assignment, how do I compute the best representation of the covariance? Okay, I can just use what's called the the sample covariance. Maybe someplace sample covariance might be, you might normalize it slightly differently or off by one, something like that. But we're just going to kind of compute what the covariance is. And it's just kind of a vector form of the variance, right? So the kind of as like an analogy, the sample mean, which is the best estimator of the mean, is going to be 1 over all the data points assigned to the ith kind of function times the sum over each x in this xi, right? X. Okay, so this is how you do the sample mean approximation. To do the, once I have this, then I can do the sample covariance as in a similar way. It's going to be pretty straightforward. Yeah, so let me try and write these a little bit different because I have a sum and a uppercase sigma. Okay, so the sample covariance, okay, we'll call it I here. this is sigma I is going to be a sum. I'll just write it this way, over x in xi. I'm still going to sum over all the data points I have, but now I just do x minus mu I, right? I'm taking the difference from the mean. Remember, the covariance is the average squared distance, or the variance is the average squared distance from the mean. With the covariance, I want to capture the vector information, so I'm going to do an outer product. Again, this is an outer product, so that means this is going to be an R d cross d. All right, so I'm going to take two vectors and I'm going to do the outer product of them, and so this give me a d by d matrix here. Okay, and so this is the sample covariance, and this is how, if I know if I know kind of the elements of cluster, I'll say for cluster xi, right, which is a subset of all of the data points. For some subset I have assigned to this function, I compute the sample mean the same way I did with Lloyd's algorithm. This is what minimized the sum of the squared distances, and then the sample covariance, which is what's going to turn out is going to maximize the likelihood function, is just the sum of these outer product differences from the mean. Okay, and so now if I have these data points, I can just estimate them, estimate the function this way, right? So then, you know, this goes to best estimate of fi equals f mu I sigma I. Okay, so I can build the best function that fits the data set in this way. Pretty straightforward. Sure. So okay. So this is, so I'm going to plug this in to update my function inside of Lloyd's step. But before I write everything out, I'm going to make another change. I'm going to go from hard clustering to soft clustering. It turns out you're going to get some inconsistency in the model you do if you do a hard clustering version of this. I could think of, I've got two distributions. Right, I've got two, it's a horrible looking Gaussian, two distributions which are overlapping. Let's make this one a different color, that are overlapping with each other. Okay, and so what's going to happen is I'm going to have some data points right here. And if I use the hard formulation, then what's going to happen is I'm going to draw some line here. And on one side, everything is assigned to, this is F1, this is F2. Everything's assigned to F1 on one side, everything's assigned to F2 on the other side. Okay, and what's going to happen is that probabilistically, there is some chance that this point here should have been in F2, right? That this guy, maybe he came from F2. That was still kind of reasonable, right? And maybe this guy came from F1, but I've hard assigned them in the other way. And so if this overlap is not balanced, then what's going to happen is that it's going to actually shift the mean of F1 too far this way and F2 too far that way, because I'm not getting the extremal points. I'm kind of chopping those off, and that's going to misestimate where the mean of those distributions is. And there are other things that go on with the covariance of these distributions. You can imagine you have two ellipses, and I have another ellipse here, right? There are two distributions that are overlapping, and I'm just kind of like, I'm taking a chunk out of one of these, you know, I'm assigning everything here onto this distribution and everything here, you know, onto the other distribution. And there's kind of a chunk missing from both of them. So my estimations of the means are going to be shifted this way and this way, and it's going to give me not going to converge to the right estimate. So instead, I want to do a soft assignment here. Okay, so I want to do a soft assignment. Okay, and now we're going to have a well-formulated way of how to do this soft assignment. We can actually write down, given these functions f1 up to fk from f, I'm going to write down the probability that x was from each fi. Okay, I want to figure out, write down what this probability is. I'm going to define that as wi of x. Okay, so this will be a weight, and these weights are going to add up to 1. Remember, that's how these are going to be our soft assignments. Okay, and so this probability, we have these likelihood functions, right? So we don't, these are not probabilities. They're likelihoods, they're probability, continuous probability distributions, but it's fine because we can factor out the normalization. We're going to define it of x is going to be f of I of x divided by sum for I equals 1 to k of f of I of x. Right? So both the numerator and the denominator have some unknown normalization term, but they're kind of canceling each other out. Or maybe I can write down the probabilities. I did have those coefficients. Those, if you remember, I had this messy term in the front here, which I didn't really want to talk about. This means that cancels out, and I can ignore it. Okay, right. So I can assign this weight for every point, and I'll guarantee that I'll have the property that for all x, that the sum of weight of I of x is going to equal to 1, right? Because I've normalized by the sum of these things, right? I've calculated all these likelihoods and I've divided by the sum of the likelihoods. So that's going to ensure that the sum of these weights are going to be equal to 1, and I'm going to get a soft clustering formulation. Okay. Okay, so I've got a soft assignment, but then I need to calculate the mean again and the covariance, and I need to kind of a weighted average of the mean. So what this means is that now my sample mean is going to be a weighted average. The sample mean is going to be a weighted average. Okay, so that I'm going to write down mu of I this is just for one of the clusters. I write this as 1 over, this is a uppercase WI, I'll define that in a second, is going to be x in x in xi in this data set, wi of x and x, right? So I'm gonna scale them by a weight. The ones that have a weight of say 1 are going to be completely in. The one that have a weight of say 0.2, they're not going to contribute as much to the mean, right? And that's going to allow me for points that are fit in here to kind of split how much they affect the mean of the green or the blue distribution. And they kind of can be partially assigned to each of those distributions. And if I do have data from both of these, I don't know where the data points come from, but they're going to kind of average out in the way I would expect. Okay, and to make this a weighted average so that I'm not scaling this in the right way, I want to divide by the sum of these weights. And so this guy is going to be I equals 1 to n of, this is going to be sum over x and x. Okay, and so I don't actually need this x sub I here, because all points might have a weight. If it has 0 chance, 0 likelihood or probability of being in one of the functions, then the weight will be 0, and so it won't do anything. So I'll sum over all the data points in each of these steps. But this will be the total weight, and that's what I've divided by here. And I'm going to do the same thing with the sample covariance, right? This is going to be 1 over the total weight of the ith thing, the sum over x and x, each of the data points, the weight of x times x minus mu, x minus mu I transpose, right? So the outer product. So the same way as before, I'm just taking a weighted average of these outer products instead. Okay, and this will give me a consistent estimator if I do this in this way instead. Okay, good. So we basically have all the pieces now. I'm going to write down the full algorithm for the mixture of Gaussians. Hopefully all the pieces make sense. And so let me try and put these together. Okay, so we're going to choose. Okay, so we're going to step 0. We're going to initialize. I'm going to kind of so some set S, we'll call these the means, mu1 up to mu k, and we'll take these as a subset of x to initialize. So this initial centers, and we'll set sigma, or these are the sigma I equals to the identity for all of them, because we don't know anything about the covariance yet. And then we'll start with the hard assignment, hard assign for each x to, we'll set weight of x equals to 1 if I is equal to phi of s of x, right? So we'll assign to the closest one the way we did. And this is just the initialization of the algorithm. Okay, and then 2, we're going to have this repeat step, which is going to be the meat of the algorithm here. Okay, and now we're going to have a for loop over all of the centers for I in 1 up to k. And the first step, we have an assignment we're starting now, so we'll start with the replacement of the centering step. This was step B before. So we'll call this step B inside of here. And so we're going to start by, okay, we're going to create the total weight assigned to each of these. And the first time through, this is just the number of points assigned to each cluster. Right, so this is the number of points. This will be our numerator. But later on, it's going to be the sum of the weights in the assignment. We're going to calculate mu I, which is going to be this weighted average. Times x, right? This is the weighted average, and we're going to calculate the covariance here, which is again going to be this weighted average. And we have the mean now, so now we can calculate the covariance. Let's see, it's weighted covariance here, x minus mu I, x minus mu I transpose, right? So this gives us the weighted covariance. And then we're going to also have, so step A, this is the replacement of the assignment step, but the assignment step is now going to be the recalculation of the weights, right, based on the likelihoods. So this is going to have let's put this up here. This used to be B. Now we're going to have A, and this is going to do a for loop over all the x and x. And what we're going to for I 1 up to k, I'm going to set wi of x equals to f of I of x over the sum of I of f of I of x, right? And this gives me the partial assignment. Okay, so this is the partial assignment step, and this is the that's what's going on here, and this step is the kind of the model building, or this used to be the centering step. So this is where we assign the best center before. Now we're doing a weighted version of this, and we're also computing the covariance. We actually get this kind of non-circular, so covariance distribution as well. Okay, and we'll repeat this until it's kind of converged. It's, you know, we could say until kind of, you know, converged. You know, and what converge means, maybe I say I'm going to do 20 rounds of this. I'm going to wait until the change in the distributions is small, you know, that I can look at something that looks like the gradient and wait until that's small. You know, but you know, some standard notion of whether it's converged or not, and what people use here is kind of varied. Yeah, so this is kind of, this is the algorithm for the mixture of Gaussians, and it's kind of just, you know, if you understand all the pieces, and hopefully I was able to explain all those, then it's a pretty kind of not too challenging extension of the Lloyd's algorithm for k-means clustering, right? In fact, if I fix the covariances to all be identities, then this is, you know, going to exactly, it's a soft assignment version of Lloyd's algorithm, and if I make it the hard version, then that's the hard version of Lloyd's algorithm. Okay, so generally, if you have a bit more data, you're willing to fit a more complex model, right? If you remember, with polynomial regression, that was a more complex model, and I might use that if I have more data. And so if I have more data, and I think I have a lot of data per cluster, then this might be better to do than the k-means formulation, because I'm going to be able to fit a more realistic model to what's going on here. But if I have a small amount of data, I might not really trust that I can really fit a real covariance that's going to be meaningful to every cluster. And I might be better off doing the kind of the k-means formulation and using Lloyd's algorithm. Okay, or if I want a hard assignment, well, maybe the best thing to do is to maybe run this, and then at the very end, I can do a hard assignment if I really need that. That might still be more accurate. You know, you might get some weird things here. Like if I look at this blue and green cluster, the assignment to the green one might not be connected, right? There might be this top piece at the top that's green, that's where there's the blue part that runs through. So there's some weird stuff that happens if I do a hard assignment, but I could still do that at the end. Okay, before I move on and quickly talk about this mean shift algorithm, I'll just give you a taste of. I want to mention one more thing. There's this idea called expectation, so maximization, are these E-M algorithms. E-M. Okay, and they take this general form that looks like Lloyd's algorithm or this mixture of Gaussian's algorithm, where I'm kind of alternating between two steps. And each step I can basically do very well or very efficiently or exactly, as in this case, but I can't do them jointly exactly, right? I don't know how to run gradient descent on here. It's a messy convex problem, but I can break it into two steps and do both of those and alternate the optimization in between those. And an E-M algorithm is a particular form of these where these steps kind of have some meaning of either, this would be called the expectation step, okay? Because the mean, you know, the mean is maximizing expectations, the maximum likelihood estimator. remember you can think of that as the expected value of the data, and the covariance is kind of like this second order expected value, right? It's expected value of the squared deviation from the mean. So that's called the expectation step, and this would be called the maximization step. Okay, and maximization makes sense if we're doing a hard assignment, then you're maximizing onto the closest possible point. Here we're doing a weighted version, but that's still typically called the maximization step. I'm maximizing the assignments, if they're soft assignments, to maximize the probability. And so with this forms of E-M algorithm, and this one in particular, you can still guarantee that it's converging, because you can write down the likelihood of the estimator you're building. The estimator is now the set of K functions, and I'm finding K functions that have a higher and higher likelihood every step. Each of these two steps is increasing the likelihood of the assignment, so the same basic proof of why Lloyd's algorithm converged can be applied to here. Now, again, it could get stuck in a local minimum, but this one is a bit more fluid, and if you do have a mixture of Gaussians, it often does a pretty good job, and people have studied more formal things you can say about this, but I don't think they give a lot of insight into what's really going on here. Great. So, okay. So I'm gonna the last 8 minutes or so, I'm gonna switch to the mean shift algorithm. But I think this is kind of the core material. This is more important. If anyone has any questions here, I can dwell on those a bit before I move on to the mean shift. So it's just going to kind of give you a taste of some other ways you can do clustering. Okay, so we're going to talk about the mean shift algorithm again, and this is, include this, it's also kind of going to be like a different sort of way of mixing Gaussians together, but through more of it's called a kernel density estimate instead. So this is going to have as input x is going to be an RD. It's not going to have a parameter k, but I'm going to have, and it's not going to really use a distance. You could use a distance, but it's going to have instead a kernel. And we're going to use the Gaussian kernel. And so the Gaussian kernel, and we're not going to have to worry about normalizing this again. So let me write it without the normalize. The Gaussian kernel, again, is defined x1 minus x2 squared divided by 2 sigma squared, right? There could be some sigma. So this sigma is given, right? So this is a parameter that's going to kind of serve the purpose as k in kind of some weird way. Not really at all like how k operates, but it's some parameter that gives us a sense of scale, or the number of how close things are. Okay, this algorithm is going to be kind of strange. What it's going to do is it's not formally going to assign clusters, but it's going to kind of move points gradually until they're all at the same spot. And when they're at the same spot, they're in the same cluster. Okay. Okay. So let me write down. Okay. Yeah. Let me say one more thing. We're going to do a different form of a weighted average. We're going to do mu of a point P. Yeah, so say we have and this will be kind of like the center of mass of the points around a point P in the data set. Okay, and this is going to be a weighted average. So of all the points, we're going to do a kernel of x onto P times the location of x divided by x. Okay, so what is this doing? I'm going to have kind of a bunch of points going to have my point P. So this is, say, P. And then I'm going to think of drawing this kernel around here. And, right, and again, this is this essentially symmetric probability distribution. And it's going to assign a weight onto every other point. Right, for this point P, it's going to have this weight onto each of these other x's. Right, and the distance kind of is, this distance is showing up inside of here, but I'm kind of doing this e to the negative distance, and that's causing it to decay in some way. And those are associated the weights of these points. And this is the center of mass of all the points nearby. So if that point P is kind of already in the center, but if I have a much more data sets on this side, then the center is going to be above P, right? What's going to happen is that I'm going to get this spot right here might be mu of P. It's a little bit different. There are more data points on that side of P, so I want to identify this mu of P. Okay, so now this algorithm is just going to have two steps. For all P in these data sets, I'm going to calculate mu of P, right, as I did here above. Right, so it's this, I'm calculating this center of mass, and then for all P and X, I'm going to shift each of these to its weighted mean. So I'm going to set the location of P. I'm going to give it this center of mass. So I'm going to change the location of this point P. I might store the original data set somewhere else just so I remember the indices, or I just have an indices or something. But I'm going to do this until kind of converged. Okay, so that's it, right? So I'm just finding the weighted center of mass based on this kernel for every data point, and then I move it towards the center of mass. I do this for all points, and then I repeat. Right, so what happens is this point P moved towards mu P, this pink point. But that's going to happen for all of these points. All these points nearby are going to kind of move towards their weighted center. And it's not going to all be exactly the same spot, but it's going to kind of be close. They're all going to move inwards, and they're gradually going to converge to the same spot over a number of iterations. And then at some point I say, okay, if they're within some distance, all points within some distance, I'll say, are in the same cluster. Okay, if instead of a kernel, I just said, I'm just going to take the average of all the points within a ball, then I'm actually I might converge much more quickly, but there might be some boundary issues because of some smoothness of this. So what people might do is actually a truncated kernel is kind of a good in between of these, where as the kernel goes out to infinity, at some point I cut it off and say it's 0. Yeah, but this is the whole algorithm. And if I have different clusters of points, right? If I have a bunch of points over here, and I have a bunch of points over here, right? And I set that, so this is sigma. You need to understand sigma to know what's going to happen. If sigma is huge, it's a whole page, they're all going to converge together. If sigma is too tiny, none of them are going to really move. But if sigma is about this, then what's going to happen is after one step, all these points are going to kind of move in here, right? They're all going to move closer together, and these are going to move closer together too, right? And so I'm going to get these points after one step, and then after the next step, they're going to move closer together until they're all basically at the same spot. And I'm going to get these two clusters of points. Okay, so this is a technique that technically does not need, so it does not need K. So it technically does not need a parameter K for how many clusters, but it can still run, and it can still kind of converge and aggregate stuff into these clusters. It's kind of a neat, different algorithm, just to give you a taste of kind of this very vast, strange world of clustering and the formulations and algorithms. This one, you know, how does this relate to kind of a probabilistic notion? Maybe there's some ties, but it's kind of very different from the one than the mixture of Gaussians that we can derive from, say, maximum likelihood estimators. So great. So I'm going to stop here and stop the lecture. And I know that you guys have homework.